In this lesson, we will delve into the comparison of planing and grinding techniques in Project 2, as well as Task 2 0.3 inches tool selection, which focuses on the characteristics, selection, and dressing of grinding wheels. We will explore the various characteristics of grinding wheels in detail, understand how to select the appropriate grinding wheel based on different processing requirements, and master the methods and the importance of grinding wheel dressing. Additionally, by comparing the features of planing and grinding, we aim to establish a dialectical engineering perspective and comprehend the significance of the inheritance of traditional techniques. In metal cutting processes, planing and grinding are two important machining techniques. Planing is a traditional method that uses a planer tool to cut the workpiece. It is characterized by relatively low machining precision and production efficiency, but it can handle complex surface shapes. Grinding, on the other hand, uses grinding wheels and other abrasive tools to process the workpiece, achieving higher machining precision and surface quality. Now, let's focus on grinding wheels. Grinding wheels are the primary tools in grinding processes, and their characteristics directly affect the quality and the efficiency of grinding. The characteristics of a grinding wheel are mainly determined by factors such as the abrasive material, grain size, bonding agent, hardness, structure, and shape and size. Abrasive. Abrasive is the main component of a grinding wheel, directly responsible for the cutting action. Common abrasives include alumina and silicon carbide. Corundum abrasives are primarily composed of aluminum oxide, Al2O3, which possesses high hardness and toughness, making them suitable for grinding various types of steel. For instance, brown corundum A has high hardness and good toughness, and is relatively inexpensive, making it widely used for grinding general carbon steel, alloy steel, and malleable cast iron. White corundum WA has higher hardness than brown corundum, but slightly lower toughness, making it suitable for grinding hardened steel, alloy steel, and other materials with higher hardness. Silicon carbide abrasives are primarily composed of silicon carbide C, which has higher hardness than corundum abrasives but lower toughness. Black silicon carbide C is suitable for grinding brittle materials such as cast iron, brass, and aluminum, as well as non-metallic materials. Green silicon carbide GC has even higher hardness and brittleness, and is commonly used for grinding hard and brittle materials like cemented carbide and gemstones. Grain size. Grain size refers to the size of the abrasive particles. It can be represented by methods such as sieving and microscopic analysis. In the sieving method, grain size is indicated by a grit number. The larger the grit number, the smaller the abrasive particles. For example, abrasive particles with a grit number of 46 are smaller than those with a grit number of 24. In practical applications, coarse-grain grinding wheels are suitable for rough grinding because their larger abrasive grains provide strong cutting force and high metal removal rates, though they result in a rougher surface finish. Fine-grained grinding wheels are suitable for precision grinding, achieving better surface quality, but with relatively lower metal removal rates. Bonding agent. The bonding agent's role is to bind the abrasive grains together, giving the grinding wheel a certain shape and strength. Common bonding agents include vitrified bonds V, resin bonds B, and rubber bonds R. Vitrified bonds are the most widely used bonding agents due to their good chemical stability and high heat resistance, which help maintain the shape accuracy of the grinding wheel, though they are quite brittle. Resin bonds have high strength and good elasticity, allowing for the production of thin grinding wheels, and are commonly used in cutting and slotting operations. Rubber bonds offer even greater elasticity and are often used to make guide wheels for centerless grinding machines and abrasive cloths. Hardness. The hardness of a grinding wheel refers to the ease with which abrasive grains detach from the wheel's surface under grinding force. It is a different concept from the hardness of the abrasive itself. The hardness of a grinding wheel mainly depends on the bonding strength of the bonding agent, rather than the hardness of the abrasive material. Grinding wheel hardness is generally classified into grades such as ultra-soft, soft, medium, medium hard, hard, and ultra-hard. When selecting the hardness of a grinding wheel, factors such as the hardness of the workpiece material and the grinding method should be considered. For example, when grinding hard materials, a softer grinding wheel should be chosen so that worn abrasive grains can detach in a timely manner, exposing new, sharp grains to ensure grinding efficiency. Conversely, when grinding soft materials, a harder grinding wheel should be selected to prevent the abrasive grains from detaching too early. Structure. The structure of a grinding wheel refers to the proportional relationship between the abrasive bonding agent and the pores. It reflects the density of the abrasive grains within the wheel. The larger the structure number, the smaller the volume percentage of abrasive grains and the greater the porosity. Densely structured grinding wheels are suitable for precision grinding and form grinding, ensuring machining accuracy and surface quality. Loosely structured grinding wheels are suitable for rough grinding and grinding heat-sensitive materials, as their larger pores can accommodate more chips, facilitating heat dissipation and reducing thermal deformation of the workpiece. Shape and size. The shape and size of a grinding wheel should be selected based on factors such as the type of grinding machine, the processing method, and the shape and size of the workpiece. Common grinding wheel shapes include flat wheels, cylindrical wheels, and cup wheels. Flat wheels are the most widely used and can be applied in external cylindrical grinding and surface grinding. Cylindrical wheels are often used for internal cylindrical grinding. Cup wheels are suitable for surface grinding and tool sharpening. Having understood the characteristics of grinding wheels, let's move on to the selection of grinding wheels. The selection should comprehensively consider factors such as the workpiece material, machining precision, surface roughness requirements, and the grinding method. For example, when grinding hardened steel, a grinding wheel with wide corundum abrasive should be selected. For processes with high surface roughness requirements, a fine-grit grinding wheel should be chosen. Additionally, the appropriate shape and size of the grinding wheel should be selected based on parameters such as the power and speed of the grinding machine. After a grinding wheel has been used for a period of time, its grinding performance may decline due to abrasive wear and chip clogging. At this point, the grinding wheel needs to be dressed. The purpose of dressing a grinding wheel is to restore its sharpness and ensure grinding quality. Common methods for dressing grinding wheels include turning, grinding, and rolling. The turning method involves using tools such as a single-point diamond or diamond dresser to turn the grinding wheel, removing the dulled layer on the surface to expose new abrasive grains. This method offers high dressing precision and can achieve a good surface shape of the grinding wheel, but has relatively low dressing efficiency. The grinding method involves using another grinding wheel or a dressing wheel to grind the wheel being dressed, and it is often used for dressing large diameter grinding wheels. The rolling method uses a roller to press against the surface of the grinding wheel, causing the abrasive grains to fracture and form new cutting edges. This method has high dressing efficiency but relatively lower dressing precision. Now let's compare the two machining techniques of planing and grinding. Although planing has relatively lower machining precision and production efficiency, it offers unique advantages when processing large and complex-shaped workpieces. Additionally, planing equipment is simple and cost-effective. Grinding, on the other hand, can achieve high precision and high-quality machined surfaces, making it suitable for parts that require high accuracy and surface quality. This tells us that different machining techniques each have their irreplaceable value. In actual production, we should not blindly pursue high-tech methods. Instead, we should analyze specific issues based on specific machining needs and choose the most appropriate machining method. At the same time, traditional techniques like planing, despite their limitations, have been developed and refined over a long period of time through accumulated practice. We should preserve and promote the essential aspects of these techniques. In this lesson, we focused on the characteristics, selection, and dressing of grinding wheels. The characteristics of grinding wheels include aspects such as abrasive material, grit size, bonding agent, hardness, structure, and shape and size, each suitable for different machining needs. When selecting a grinding wheel, factors such as workpiece material and machining precision should be comprehensively considered. After a grinding wheel has been used for a period of time, it needs to be dressed. Common dressing methods include turning, grinding, and rolling. In addition, by comparing the characteristics of planing and grinding, we have developed a dialectical engineering perspective, understanding that different technologies each have their own value and should be analyzed based on specific issues. We also appreciate the importance of preserving traditional techniques